Okay. Hi. Thanks everybody for listening to the last talk before dinner. This talk will be a little bit different from what we had before, but maybe a bit related to what Claudia Felser already discussed earlier this week. So I'm actually running a chemistry group at Princeton. So we are solid-state chemists, and somehow all my pictures are stretched. Well, it's okay. Anyways, so we're working on finding new topological materials and also looking at new 2D materials. However, because this is a topological matter school, I'm mainly talking about the topological materials. And my first lecture will mainly be about introducing how chemists kind of think about these ideas. How do we identify a material? How do we look at structures? How do we count electrons? Like, what kind of feelings can we get? And can that be predictive in finding topological materials? So this is basically the logo of the group, and that's our motto. It's a brain with one half thinking of physics and the other one of chemistry, and kind of finding the interface of this. And I hope this lecture will also give you an idea that looking interdisciplinarily can sometimes be extremely useful if you want to move forward with your projects. Well, this is the minute. So basically what we do is that we try to connect the crystal chemistry and structure with an electronic structure of a compound, and this links to its properties. And so for this, you need to know several disciplines because you need to understand every corner of the triangle to use this effectively. And so you might know about band structure really well, or you might know about transport properties really well. But if you don't really understand what a crystal needs to be built up, then it's difficult to make the links between these ones. And so by focus on the lecture, we're kind of giving a short overview on principles of solid-state chemistry and reviewing the most used rules and guidelines so that there's an understanding of what types of crystals can be stable. So solid-state chemistry is a field, and most of solid-state chemists do not really look at topological materials. There's just a few outliers who started doing this. So most solid-state chemists are interested in crystal structure and why structure forms in the way, and also how to relate it to properties. But often they're thinking about batteries or like lots. I mean, your iPhone is basically an homage to solid-state chemistry because most of these materials have been linked to properties and developed by solid-state chemists. And so in understanding the structure and when a structure forms is very important for this. And chemists have been successful figuring this out by making such things as structure maps, where this is, for example, one which is dependent on size, can be dependent on different factors, where you have a phase which all phases have this kind of composition of A, L, and P2S6. And the A atoms are plotted on one axis, whereas these are the A atoms and the Ln atoms on the other one, and there the sizes of them are plotted. And so then you see you get different colored areas, and in these are different space groups adopted by the structure, so completely different crystal structure can just form based on the sizes of the atoms. And this is my first important message I want to tell you, is that you cannot randomly substitute something isoelectronic and assume that it will take the same crystal structure. Okay. And this is another example of this. So here I drew 5 different crystal structures of different compounds, and they all have a 1-to-1-to-1 stoichiometry. So they're all ternary compounds, they all consist of 3 elements, and they have completely different structures. And also they do have completely different properties. So some of these are insulators I drew here, some of them are metals. So it really changes a lot what the structure adopts. And so there are 3 things we can use to assess and kind of get a feeling which is the most likely structure to be adopted. And these depend on electron count, sizes of the elements, as already briefly mentioned, and the type of bonding between the atoms. And all 3 of them, I really briefly want to give you an idea of what that are. Periodic table, most famous or most favorite thing from any chemist. I don't know if you guys don't get that, right? We get the mug with the periodic table, and like every morning at breakfast I can look at it if I want to drink my coffee. Anyways, so that's a side story. The periodic table tells us how to count electrons, and I put the numbers in colored above each column, like how many electrons you should count for for each element. And you can just take this, and then you take any kind of compounds and add up the numbers of electrons. So for example, we could do this for sodium chloride. And so we have 1, sodium is here, we have 1, we have 7 for chlorine, we get 8. And so whenever we have 8, we fill all the S shell and the P shell, because the total count until here is 8. So that means we have a filled shell system which will be insulating. And you know sodium chloride is your table salt, so it's obviously insulating. You all see it as a transparent solid. So if you have a bit more of complicated structures where you have some atoms double, like calcium fluoride, then you will have to divide by the number here of your most electronegative element, like fluorine in this case. So this is your anion, which takes the electrons. So if you count calcium fluoride, you would count to 16, but since you have 2 fluorides, you divide by 2 and you get 8 again. So you again have a charge balance system, and calcium fluoride is actually it's a really nice gemstone. I should have put a picture of it, but I forgot. It's like this green-purple stone, and it fluoresces, but it's obviously insulating too, because it is like transparent green. Anyways, so it's obviously an insulator as well. And so you can extend that to much more complicated systems. So this is a slide I stole from Claudia, where she loves Heusler compounds, these kind of ternary materials, and there you can use the same kind of electron counting and figure out when they're insulators or at least semiconductors, so when their electron count matches up. So gallium arsenide is a known semiconductor. Everybody knows it. It has 8 electrons. But you can also go further and substitute gallium to lithium and magnesium. So this has 1 and 2. So then you add up to 8 again, and you again have a semiconductor. Or if you want to include transition metals to this, then you have to add up to 18 electrons, because you fill your D shell as well, so you have 10 electrons more. And again, strontium, platinum, antimony has a band gap, so it's a semiconductor. And if you go to heavier elements, you can get 0 band gap materials, like mercury telluride, a topological insulator, but it's still, like the bands are just touching, so it's still a charge balance account. So this kind of counting gives you an idea, can I have a semiconductor, or will it be a semi-metal? But it's always kind of you will have the same amount of electrons and holes in the end, even if the bands overlap. However, if you just count to 8 or 18, then a kindergarten kid could do that and predict all materials. So sometimes nature isn't so nice to us, and there are some examples. And these are called Zintel phases. And I just want to give a little anecdote of the first time I accidentally came across a Zintel phase, and I didn't notice it at the beginning, but it was very confusing. So it was actually a friend of mine in graduate school, and she made this phase. She said she made lanthanum gold antimony 111. And I happen to work on these 1-on-1 phases, and I happen to know that it's extremely rare you make one which doesn't have 18 electrons. So I first of all was like, no, something is wrong. Like you didn't do it right. And I said, so I think lanthanum gold tin can exist because tin has 1 less than antimony, and then I calculate the density of states and see, it has a minimum here, so it's a semi-metal. So it said 18 electrons, that's all great. But she was like, no, I definitely had 1 to 1 to 1. And I have 19 electrons. So we looked really closely at the crystal structure, and then we noticed when we were solving the crystal structure from the fraction that the gold atoms actually come awfully close to each other in the structure, and this doubles the unit cell. So normally a 1-1-1 compound with this would have this kind of unit cell here, but it doubles it, and the gold atoms get in close contact. So this means that there's a bond formed, a chemical bond, covalent bond, between 2 gold atoms, and so there is 2 electrons paired. Double formula unit, or 1 electron per gold, is localized in this bond and doesn't count towards your electron count. So this electron per gold atom will be localized in the core states, and it will not appear in your electronic structure calculation. And so if you do DFT and you input this structure into your code, you also find that it has a minimum at the Fermi level. Okay, so just blindly electron counting doesn't always work. You also kind of have to look how the structure looks like. And I already said this is a common phenomenon, and it's called Zintel phases. So lots of phases. So these are phases which are not electron precise, but they're known to be semiconducting. And by the way, they're usually trivial semiconductors, but I'll talk more about this later. So the mostly used example is calcium silicide, so it's calcium Si2. And if we would do our electron counting here, we would count 10 total, and we have 2 silicons, so we divide by 2, we get 5 electrons per silicon. So that's not 8, right? So it's completely off. So we would think it's a metal. But actually, if you look at the structure, we see each silicon is bonded to 3 other ones. So in this case, it's a little bit different. There's no extra electrons that needs to go away. This time, they're electron deficient, and they're forming bonds to kind of share electrons and therefore fill their shell. So this is the same principle as why molecules are formed, and carbon likes to form 4 bonds and everything. So it's basically what organic chemists do all the time in an inorganic compound. So we really, really need to look at the crystal structure to count electrons correctly. And so I just gave you 2 examples. One was a polar cation, where I want to get rid of electrons. I have more than the count gives. And the other one was a polar anion, your silicon network, where I need to add some electrons to make the count match. And so there's a simple rule. Like if your valence electron concentration is greater than 8 or 18, you have a polar cation. And if it's smaller, you have a polar anion. And actually, there's even a rule in chemistry textbooks, if like some solid-state chemistry textbooks at least have it, that you can calculate your bond order from this. So let's say you assume your phase should not be semiconducting. Sorry. Like you counted your electrons and you found 5 per silicon. And you're like, oh, it's weird. Let me assume it's semiconducting. So you can subtract this 5 from the number 8. Your bond order will be 3, and then you can look in your structure if you actually find the free bands, and if these 2 things are equivalent, you know you have a charge balance system, whereas otherwise you actually might have a metal. Okay, but already in the beginning I said electron count is not everything. Size matters a lot by predicting structures. And here's one more of the structural maps just based on size, where you have different phases based on the different sizes of the atoms used. And I just want to point out that here the structures are really, really different. So here we have a cubic network, so there's a cubic structure here. And then here we have a layered graphene-like structure. But they're all isoelectronics compounds. They just go up and down in a periodic table, and we get completely different structures based on the atomic sizes. And you can also use pressure if you have a material close to a boundary to push it from one structure and another one in this phase diagram. Okay, so this is also a way you can try to predict when a structural transition should happen under pressure. And so there are also some rules for sizes, not so much in intermetallic compounds, but in oxides and fluorides. There is a rule set called the Pauling rules. It's also a very old rule, and it's really based on geometry by measuring, so as Claudia mentioned, in a crystal you always assume that the space is filled and all spheres are densely packed. And then you can calculate how the size of a hole is between all your atoms. And from this you can derive some ratios of cation to anion radius and see what kind of coordination is possible so that your cation literally fits in the space of the anion. So your anion is always the big one. It fills the space. The cation goes in the small holes. And you can really calculate, does it fit? And so you get these numbers. Okay, if it's larger than 0.7, you get a cubic coordination. If your ratio is in between 0.4 and 0.7, you get an octahedral coordination. And if it's smaller than 0.4, you get a tetrahedral one. And I come back to this later, why this is very important if you want to predict new materials. Because if you make something up and you say it violates the Pauling rule completely, it's not going to form. Okay, so you don't even need to do DFT or stabilization. You can just look at the ionic radii ratio. And so there's this, here I put this website here. It's a very nice one. You have a periodic table, and you can look up all your cationic ionic radii, and you can see if anything you came up with makes any kind of sense before you check any phonon modes or do a complicated calculation. Another really important concept is electronegativity difference. So far I talked a lot about charged balanced materials, and these appear usually when I have a salt-like structure, so a very ionic compound, and ionic compounds happen if one of your elements making up the compound is from this area of the periodic table where electronegativity is small, and the other one is from up here where it's large. So this is how electronegativity goes. And if I have compounds which are made either of only one element or of two which are close to each other, then it's more likely that they form metallic or covalent bonds and not ionic ones. So this is also some kind of feeling you get. And very important is whenever you have salt-like structures, they have to be charge balanced. Your electron count has to match. Otherwise, maybe not. Okay, so basically, just from chemistry, we can just get an intuitive, very simple picture of the electronic structure. If you can at least get, is this a metal, a semiconductor, or an insulator? So if the electron count doesn't match, like in a copper beryllium account will be a metal. If the electron count matches and goes to a charge balance system, like 8, it can be a semiconductor or an insulator, and for this we kind of include the electronegativity difference. So it's large here, so we have a large gap, and small here, so we have a small gap. So some kind of intuitive first prediction of an electronic structure. But what we also like to do is looking at common structural motifs in crystal structures. So this is an example for iron-based superconductors, and they all have this completely sharing structural network here of this edge-sharing arsenide or iron selenide tetrahedra, and they're all superconductors. And so superconductivity is a very common way for solid-state chemists to look for these common motifs, because theoretically it's very hard to predict a superconductor, so these structural things really matter to find more ones. But I will argue later that you can also look for structural motifs to find topological semimetals. Okay. Let's now move to topology. So this is a timeline roughly of what happened in the field. I might have missed a lot, and I ended in 2016. But the point I want to make is that I will mostly focus on what happened 2014 and later, which is topological semimetals. And so this is basically a little bit of a discussion of this review article I quickly want to advertise. So I was asked to write that about a year ago because of exactly these lectures I've been given. So I was asked to put my chemical intuition into an article to explain to chemists how to find topological materials. And I said, yes, but I just want to point out I don't like the word chemical intuitions, because that's not an intuition. This is based on rules and that have long been established. So it's not, intuition kind of sounds unscientific, I think. Anyways. For this, I kind of quickly want to review how chemists view an electronic structure, because we do that different from what you're used to. You say, okay, it's a curve of energy versus momentum, and so you kind of have to find a Hamiltonian which describes the energy momentum dependent or something. In chemists, you can scare away with any Hamiltonian, and so I'm not going to show any in this talk. The chemist says, let's look at the orbitals and let's draw pictures and have like a visual aid on a band structure. And I mean, Claudia already mentioned this a little bit. I just want to review this shortly. So Roald Hoffmann, she had his photo, I don't have his photo. Roald Hoffmann is a very famous organic chemist. He actually won the Nobel Prize in Chemistry for organic chemistry, something completely not related to this field. But what he also did was he wrote this amazing article, How Chemistry and Physics Meets in the Solid State. And this paper really nicely, intuitively explains to chemists how to look at the band structure from the molecular picture we used or trained to look at. And basically what he says is like, okay, let's start with the simplest thing we can imagine, a linear chain of hydrogen atoms. So we just have s orbitals in a chain. And then this is our unit cell here, one atom, one chain. And so at the gamma point, if you look at the Bloch function, you will see that all atoms will have the same phase. So the colors here, the white color means phase is positive. And then at the pi over a point of the Brillouin zone, the phase will alternate. So this is a negative phase and there's a positive phase in the colors. So therefore, this must be higher in energy because these are not, there's no bonding interaction here, it's anti-bonding, whereas this is low in energy. So this is the band structure you get. And then he says, okay, as chemists, we know hydrogen doesn't exist in a linear chain. In reality, it makes a diatomic molecule. So let's understand why it does that. And so if you know you're going to lead, like your goal is a diatomic molecule, the first thing you have to do is double the unit cell here, because then we need to have 2 atoms in the unit cell. So if you just double the unit cell and you don't change any kind of distances between the atoms, what you will get will just be a folded version of the band structure because we doubled our real space, so we have to small our K space. And then if you draw the orbitals at all these points, you will see here that this point is degenerate because you have 2 bonding, 2 antibonding, 2 bonding, and here you kind of have the same. But now if you start distorting this and actually form a bond and form the molecule, these, you see here in this picture that here you have the 2 bonding closer to each other, and then the 2 and the antibonding farther away in the gap, and whereas here you have within your unit cell, you have a bonding and an antibonding. So what happens is that this state is lowered in energy and this one is higher in energy. And so therefore you open up a band gap and you have an insulator. Everybody knows hydrogen is an insulator. And actually this is a very simple model of a pious distortion, okay, which is happening in this chain. All right, why I'm explaining you all this kind of thing. So this brings me to graphene, which I think is the simplest electronic topological semi-metal, and simple ones to describe. And I know you can write out tight bindings and then accurately describe it. And how I describe it to you is a chemist viewpoint now, and it's not fully accurate. I'm not going to claim it, but it's an intuitive picture how to understand it. Okay, chemists would we don't really look at the full picture of a structure. We look at this one atom and its electron count. So if you look at graphene, we're going to look at one carbon atom, and we say, okay, it's sp2 hybridized, forms 3 bonds here, and then it has a pz orbital, and then there's 1 electron left in the pz orbital. So if we would draw a band structure, we draw sp2 manifold, and we say this is completely filled because it's all bonded saturated. And then we have a pz orbital, so we always draw it in these energy levels, and this has 1 spin in it. And then, okay, we also know it's not really just a molecule, it's an extended network, so we have to extend it to bands. And then we have a fully filled sp2 band and a half-filled pz band. And so then if we would draw roughly the Roald-Hoffmann band structure, we have 1 half-filled band. So it would kind of look like what we draw for a single chain of hydrogen. I know this is hexagonal and there's a little bit of different symmetry, but let's ignore this for now. Okay, so we have a half-filled band. So this picture, this is the intuitive chemist picture, describes why graphene is metallic in the sheet, but it doesn't explain to you why it's a topological semi-metal or why it has a Dracon. Okay, and the reason is because we ignored what is actually the unit cell, and if we draw the unit cell of graphene, we see we have 2 atoms in the unit cell. So okay, Roald-Hoffmann told us what to do. If you have 2 atoms, just fold the band structure. Okay, let's do that. So if we fold it, and then we actually extend our drawing to 2 unit cells, you get a very intuitive picture of the electronic structure of graphene. Okay. Just at the next step, the distortion that happened in a hydrogen atom does not happen in graphene, and so we're actually done with our picture right here. So why does graphene not distort? Okay, so chemists like to draw the pi orbitals in graphene like with these rings. And with this they indicate that they're delocalized. So the pi electrons delocalize over the whole carbon network, and that stabilizes. This gives you an extra energy. It's called aromaticity, an aromatic energy, and that stabilizes the graphene. And it keeps the hexagonal symmetry. And so basically a chemist says this aromatic delocalized pi stabilization is what causes the electronic structure of graphene, and physicists say the hexagonal symmetry or the symmetry protection causes this, and it's the same thing, right? Because one determines the other. Okay. The thing is that this kind of aromatic delocalization is very unique to carbon. Carbon is known to do that. Carbon is known to bond to itself. It's known to have pi bonds that delocalize. No other element is known to do that. Okay. So actually the reason we are all carbon-based has something to do with this. And the reason that I'm not spontaneously combusting right now is that I'm mostly made of carbon and nothing else. Okay. All other elements are really highly unstable in this configuration. And so, because if you would do anything to distort this, like either form double bonds, like in this way, you open a trivial gap. If you make it out of 2 elements with different electronegativities, this is boron nitride, you have a trivial gap. If you somehow buckle it and form a 4th bond, you open up a trivial gap. Or, well, not always in this case, actually, you can trick it, but then it's a very different kind of inverted band gap, not based on the same version of graphene. And that's also the reason why it's so hard to make all these silicines, germanies, and something. Whenever you put it on a substrate, it's going to strongly interact with the substrate and going to mess up this delocalized electronic structure. Okay, so before I go on, it's just, okay, so I thought for some time when I started my career in this, I thought, okay, I'm never going to find a graphene analog in inorganic chemistry. And so this is done, this is special to carbon, and we should just focus on other direct semimetals and keep going. But that's actually not true. And I'll come to this in a minute and tell you how we can trick nature and use inorganic chemistry to find similar delocalized electron systems in inorganic solids. First, I want to differentiate that graphene is, in my point of view, a different type of 3D direct or 2D direct semimetal or whatever direct semimetal than cadmium arsenide and the other known ones. Because in graphene, I just said it's the pi bonding which causes the linear dispersion and the band inversion. So the bands are inverted here between pi star and pi. So it's actually a bonding which causes this. Whereas in cadmium arsenide, and I'll show you lower, it's actually just a low-lying s electron of cadmium. So it's just one atom that's causing the band inversion. So I call these ones atomic 3D direct semimetals and these ones molecular ones. And what I want to point out is that these ones are way superior because this is just a rough sketch, but in graphene, this band inversion energy, like the region these linear bands span and invert is huge on a huge scale. In cadmium arsenide and sodium-free bismuth, the other ones is tiny. Also, there's also a problem for a lot of TIs. Okay, so this kind of molecular type of band inversion is what you want to get the good materials. Okay, so we said it's based on bonding. So what type of bonding do we need? So I said, okay, we have 3 types of bonding, most commonly in chemistry. One is ionic bonding. We discussed it, but we said sodium chloride is an example, and even gallium arsenide. Most of these are not inverted. Like this kind of bonding doesn't cause band inversion. It usually causes trivial gaps. Then we have covalent bonding, which can happen between the same elements. And here, this is a rough sketch of diamond or silicon. But even these, like we know silicon is trivial, it doesn't really cause a band inversion necessarily. And so this is because here our electron count matches. In silicon or calcium silicide, what I had, the electrons match in this way that each of the bonds here have just 2 electrons between 2 atoms. And this is called a 2-electron, 2-center bond. So we have 2 centers and 2 electrons in between it. Then it's fully charged balance, likely to be trivial. And then we have this third kind of bonding like we have in graphene, this delocalized ones, and we get the inversion and the crossing. And so I was wondering, because here we have 2-electron, 2-center bonding, but from chemistry we know there are materials which have something which is called 2-electron, 3-center bonding, or 2-electron, 4-center bonding, which means that these 2 electrons here are not shared between 2 atoms and thus localized, but shared between 3 or 4 atoms, and therefore they are delocalized a little bit throughout the system. So is this the kind of bonding we have to look for? So this gets me to my favorite compound, zirconium silicon sulfide, because I argue in this case, here this is the case, and we have a topological semimetal which is based on bonding. So zirconium silicon sulfide is a tetragonal material. Here's the structure. And its most promising feature is this network here of silicon atoms. And here we have basically silicon atoms which are close enough to each other in space that there's some overlap between the orbitals, and you can call it chemical bonding. So the distance is close enough that the bands won't be fully flat. And so if we would do electron counting on this material, it wouldn't work. So we have zirconium, chemists would say it's roughly 4, it's usually 4+. And then silicon is usually 2- charged. So then in order to somehow match this, you get silicon 2-, which is not a common oxidation state of silicon at all, and it doesn't add up. So like this total electron count would be 14, so it's neither 18 or 8, it just doesn't really work. So then there's also another aspect of the Zintel concept what I made is that if I have an atom which is charged, it only works for main group elements, by the way, and I just add the 2 charges, I move on the periodic table to the right, and this atom is going to behave like this element. So if I have silicon with 2 negative charges and I go 2 to the right, I end up at sulfur. It means silicon should behave like sulfur in this compound. And so sulfur usually forms 2 bands and has 2 low pairs. So sulfur has 6 electrons. It uses 2 of them to form bonds and 4 of them to have 2 lone pairs. So that means, in our case, if our silicon is supposed to behave like sulfur, then it should form 2 bonds only, but it forms 4 bonds here. So it means it has only 2 electrons to form these 2 bonds. So that means we have only half an electron per bond. So we do have some kind of delocalization or a 2-electron, 5-center bond right here where they are. Okay. So if we calculate the electronic structure of zirconium silicon sulfate with DFT, we get linear bands that are crossing, and they do that over a significant range of energy. It's not as large as graphene, but much larger than cadmium arsenide and sodium bismuth. So it gives us some kind of indication that this is based out of bonding. And it crosses it several times in the Fermi level, so this is not a normal direct semi-metal, it's a direct line node or nodal line semi-metal. I'm not going, so it just means the Fermi surface is a line instead of a point. So let's try to understand why this happens. So now we can do Roald Hoffmann's band structure drawing, but for a square net, because we have a square net of silicon atoms. So we can look at S and all the free p electrons on the square net. And so we have a gamma, x, and m point in our square 2D Brillouin zone. And basically, the Bloch function changes the sign once along one direction on the x point and along the kx and ky direction on the y point. So if we look at the s orbitals, see this is all bonding. So here it's lowest in energy. Here we have bonding along one direction, anti-bonding the other one, so a bit higher. Here everything is anti-bonding, it's more higher. And we go back to gamma. So we just get this shape of an S-band. And we can do the same for PZ, and they have the exact same orientation. It's just a little bit flatter because pi bonding is weaker than S bonding, so we get the next band. And then PX and PY are different, so we can just draw the orbitals in the same way, and we get this kind of band structure. And you get the same thing if you put in a simple type binding model. This is just chemistry way of making type binding. Okay. Yeah?
Draw those graphs without using type binding? Or?
Yes. You don't need type binding. You can just draw your orbitals and look where the bonding is. And you get that.
But how do we get those shape of the graphs out of the
Well, I mean, I just draw, so here I draw p orbitals, right? And in gamma, they're all in phase. So I can see they're anti-bonding here, and they're kind of pi bonding here. Pi bonding is weaker than sigma bonding. And then here I have strong sigma bonding in this direction and pi bonding here. So this one is lower at x than at gamma, so I go down. Okay, so it's a kind of correlative sketch. It's not, but in tight binding, it depends what kind of hopping you choose to get the steepness here. Just draw it based on feeling. Okay, so anyways, and also like I chose to put the PZ orbital on this energy. I mean, you can put it down here. It's more from chemistry. I know the S is the lowest in energy, and then the PZ. So I kind of it's a little bit hand wavy estimation. But as I said, if you put up a tight binding, you also choose all your hoppings and your starting energies. So if you have no reference system, you come up with the same. Okay, so this band structure here doesn't really have nice direct crossing. So it doesn't really explain us why we found this in zirconium silicon sulfide. And so the answer is again folding, because if we looked at the crystal structure again, so the sulfur square net actually made this large kind of unit cell, but the silicon square net had a smaller mesh. So this has a different kind of unit cell. So in order to understand the electronic structure, we have to use the larger unit cell, because otherwise we don't fit in the sulfurs. And so that means we again have to fold the band structure. And so this is how you fold in a square Brillouin zone. And it's basically like rotating around this one and folding, and rotating here and folding, and this then is drawn here, and this here, sorry. So you need to stare maybe a bit to see it. But then this is just this picture folded. And you see here, you get a really nice crossing along gamma m. And this crossing is guaranteed from the px and py to be there. You also get it in a tight binding. And then here I did get another crossing here between px and pz. But this is only because where I chose my energy level of the pz. And I chose it to cross because in zirconium silicon sulfide it crosses along this direction. But this is not purely based on the square net model. Okay? But this one is guaranteed to be there. Okay.
Why do you have lines between x and m? Why do you have lines between x and m?
Lines between...
Here,
you just connect because you know that they have to connect between x and m again, right? So you fold and then you connect the ends. Yeah. Okay, so but now the question is actually, not every material with a square net will be a topological semi-metal. It depends on the filling. So for example, the prototype of the material with the structure type of zirconium silicon sulfide is called PBFCl. And this one here, the fluorine sits on the square net, and the fluorine gets an electron from lead to have 8 electrons and be happy, and your filling is up here, and it's just a trivial insulator. Okay. But because in zirconium silicon sulfide we have this weird electrons count of 6 electrons per each silicon, our Fermi level will be here. Note that I counted for 1 silicon, and this is now a folded band structure, so you have to count to 12 to understand it here. So then our Fermi level is exactly where we want it. Okay. Yeah.
So how to understand that the Fermi level will be precisely at the direct point or whatever point you have there? The semi-metal point? How to get it from chemical consideration?
Okay, so because we have 6 electrons per silicon, so that means we fill the full S band, so it's folded, so just divide by half, right? We fill the full S band, we fill the full PZ band, and we fill half of the PX and the PY, right? So we have a half-filled band here. I'll come back to this later. This is actually a very special thing. Actually, good point. Because half-filled band is a problem, and therefore these materials also have a stability problem. So tomorrow, or maybe later in this lecture, I forgot when it's coming, I will talk more about half-filled bands, which are actually rare to happen. Yeah? 5 more minutes. Oh, okay, so I don't know if I will get to this at all. So what many of these compounds, which are isoelectronic to zirconium silicon sulfide, they don't have this square net. They actually distort in these kind of zigzag patterns and are in different structures. And so this is actually what you would also imagine from the Zintel concept to form, because here each silicon has 2 bonds, right, like it's supposed to have. So this is the Pierce distortion that happens to do what chemistry predicts. And even if you look, so this is a crystal orbital overlap curve population, crystal orbital overlap population curve. Chemists love this. I don't know if it's not so familiar to physicists, but what it is basically is a density of states, but plotted in a way that bonding contributions are plotted to the right and anti-bondings are plotted to the left. And so in zirconium silicon sulfide, if you look at the silicon-silicon overlap, it's actually strongly anti-bonding at the Fermi level. So it really indicates it doesn't want to form this network. The reason why it's still stabilized is that actually, the zirconium 4+ oxidation state is more formality than reality, and it still does have some d electrons. And this zirconium silicon bonding, like zirconium d states to silicon, is so strongly bonding that it overcompensates everything of that. Okay, and so if you look at the bands and with more detail, you see that the linear bands are composed of silicon p and zirconium d states. So it's kind of these zirconium d orbitals that help you stabilize this. And this is another important message we need to think of, because sometimes we need something to stabilize something which is completely chemically unstable to avoid the distortion which is happening otherwise. Yeah?
Where did you get that picture from?
This?
DFT or?
Yeah, this is DFT, I think. I asked a friend of mine to run it, yeah. Yeah, you could also draw it intuitively with counting, but this is more accurate than that, yeah. Okay, so we were kind of interested if we find more of the compounds where the square net is actually in a non-distorted, isolated fashion, has the electron count where you can have it. And so it's a work of my postdoc Sebastian. You actually did a really annoying, like by hand data mining approach, because we are not as advanced as all you guys who can just like computation do it. So there was a lot of work. And so he looked up at all the isostructure phases. So he only looked at the ones which are not distorted, where we know the square net is there, and which are reported in this structure, or in the PBFCL structure, how it's called. And so here's a periodic table. There are more than 500 compounds. And so this is the different elements. So the silicon element, which is the square net, is what we put in green. And all these elements can sit on the positions. So there are lots of them. And then we define some geometric constraints to kind of filter this data out and to understand when we have a topological semi-metal and when do we have an insulator. And so basically, my postdoc defined this, what he calls the distance d, which is the distance from the green square net to the next atom in the structure. So this can be either dm or dz, because sometimes z is lower and sometimes m is lower. And so you can see from this picture, with just Pythagoras and your atomic coordination, you can calculate this distance. And another important distance is the one within the square net, so the distance between the 2 silicon atoms. So he made a plot of all the compounds where you put the distance ratio, so the square net over the distance of the square net to the next layer on one axis. So basically, if this one is smaller than 1, that means your square net is rather isolated in the crystal structure because you have a smaller distance between square net atoms than to the next layer. So it's more a 2D material. And up here we have more 3D material. And then, okay, all these gray points are ICSD data points of these compounds. All the green ones are the ones where we trusted the materials project enough to look up the electronic structures, and the gray ones are the ones where we think the data there is not reliable. And the shape of the points indicate the property, and the color indicates the electron count. So all the green points here are charged balanced, and they have 0 or 8 electrons, and they're mostly all of them are insulating. The few metallic examples is just because they're like semi-metals. Like we said, we have 2 overlapping shells like in mercury telluride. So all these, and in all these, the crystal structure indicates that the square net is not isolated. Okay? And then down here are the ones which have an isolated square net. And then we have some which 7 electrons on the silicon or on the X atom, which doesn't match the electron count we want, so they're metallic. And then we have all these ones with 6 electrons, which is the count we want. And they're all clustered together just by geometry. I've already thought this is a cool result, that you can already find them based on this. And then you see the triangles are confirmed topological semimetals in this family. And the diamonds are some compounds which are metallic. And so we called them metallics, so they might still be topological based on the classification. This is all in the catalogs, but we called them metallic because they were other bands were interfering with the steep band. So it wasn't so clean and beautiful as in zirconium silicon sulfide, where the triangle all have beautiful band structures. So these are not topological, they're just dirty topological. And so you can use chemistry, and that's my last minute to explain this, and then you can stop, to understand why. Because, okay, so in zirconium silicon sulfide, we had zirconium 4+, and we said the 4+ is a good oxidation state to stabilize the square net with the d electrons. Then, if the atom, so the atom, if it's 3+, we basically have 0, like we have only these 2 examples here of lanthanum and cerium antimony telluride, and all the other ones distort. So 3+ is not that good of an M cation to distort the structure. But if we have 5+, like in these niobium compounds here, niobium, so these metallic ones, or like dirty ones, here, they would have a 5+ oxidation state. So there is like too much of the good. There's too many. So if 4+ is already only a formality of an oxidation state and not fully there, 5+ is even worse. This niobium will never be 5+, so it has a lot of d electrons still floating around, and they mess up your band structure. Okay, so you can use this plot combination with just counting and looking at electrons. You can find very easily your clean topological semimetals in this family. So this was just one structure type, just for an outlook. We also did that for other square net structures. So here's one. So it's basically the same structure, but it has an extra square net stuffed in. And so then we have 2 square net parameters for each compounds to plot. But we found then for every confirmed topological semimetal in this structure, one of the square nets, the parameter lies in this distance ratio below.
Sorry, because now you have manganese?
Yeah, yeah, exactly. But it's actually, yeah, these are magnetic. I mean, they're known, they're investigated. So there is magnetism, there are topological bands, but so far the interference isn't really clear. Actually, if you look at this article, we reviewed everything. It's on archive. You can look it up. The point I wanted to make, so most of the time it's the bismuth net here, which lies down in this area. But one of them is here, and they're topological. And then if you looked at some insulating counterparts in the structure type, both of the square nets move up there. Okay, so this is a very predictive way. And I wanted to talk about atomic ones, but I think I'm done, right? Sorry. Yeah.
So just take Leslie.
You cannot just break inversion symmetry in a given crystal, right? So then you have to start doing the same kind of map with inversion asymmetric compounds, and maybe you find something.
And is there any intuitive way to picture that in terms of the orbitals?
No, oh, no, well, yeah, I mean, well, the way we drew it, the bond, actually it is in my, I drew that in my review article, in the first one I highlighted. So the thing is, when we draw this, we draw spin degenerate bands, right? But then if you break inversion symmetry, you know you lift the degeneracy along certain lines, right? It's a Dresselhaus effect, so you can somehow draw the intuitive picture first and then split them. But the thing is that you don't really know the magnitude, so then it becomes a little bit fishy. Depends on spin-orbit coupling and everything, if the splitting is large enough, right? Yeah.
I didn't catch where you developed the criteria for topological state in that.
Oh, so just if I see the band crossing in, like in zirconium, silicon, sulfate. Yeah, okay, so these are defined weak TIs. I went over all this. Sorry. Yeah.
You were talking about the degenerated states, and then suddenly it was topology.
Right, yeah, okay. So actually, it's fair to say topology in this thing, because other people proved that these things are stacks of weak TIs in the 2D layer, but I didn't care about this. I just looked for band crossings. Because, I mean, even if you have an even number of band crossing, you still have band inversions, and you can start going from there to something.
Any more questions? How would you find the isostructural compound with these 5 families? How do you characterize them?
Oh, you can just go to, yeah, you just go to the ICSD and you search for structure type, and then it pops all up. You know that it was defined by crystallographer.
The same space group, the same sequence of bipole positions?
Yes, exactly.
Okay, so let's test clarity again.